we'll get started. And so it's now week 6, and I hope everyone is doing great. All your classes are now over halfway over, and now we're taking a strong shift away from all of this R stuff into, I mean, there's still going to be R stuff, don't worry about that, but we're going to take a strong shift into the statistics part of computational statistics, okay? And on the first day of class, I kind of said that computational statistics is, using the computer, using these computationally intensive methods to help us answer statistical questions, to help us answer these questions about probability and statistics. And so, in order to do that, we have to understand how R works. And in particular, because a lot of our answers will be numeric in nature, it is important that we understand how numbers work on the computer, okay? And so today we're going to talk about floating point precision. And specifically, we're going to look at the IEEE 754 standard on floating point precision, okay? And so, this was a standard developed in like 1985, and then they revised it in 2008. This is how these electrical engineers said, hey, when we want to have our computers be able to compute numbers and do math, this is how they should do it, okay? And this is implemented at a hardware level. So, pretty much all of your computers have Intel chips. Maybe some of them have AMD chips, but all your Macs, they got Intel chips, and most PCs will probably have Intel chips, and this is implemented at a hardware level. It's not something specific to R or anything like that. Doesn't really, whether you're using C or R or Java or whatever, and you're asking for numbers, this is happening at a hardware level, okay? And so first maybe we have to talk about real numbers. So throughout your academic career, you've been dealing with real numbers, okay? Whether they be integers, rationals, or irrational numbers, you've been dealing with real numbers. I mean, maybe some complex numbers, but in general, real numbers, okay? And the thing about real numbers is that there's an infinite number of real numbers, and between 0 and 1, there's an infinite number of real numbers, and between any two numbers that you pick on the number line, there's an infinite number of real numbers. Now, we cannot have the computer figure out the infinite number of numbers, okay? Computer, today your computer might have 8 gigabytes of RAM or 16 gigabytes of RAM, or, it might have a lot, but that's still not infinite, right? And we cannot be able to store a number with an infinite number of decimals, because that would also require an infinite amount of RAM, and that's just not possible. And so the electrical engineers said, okay, well, we'll just represent what we can with a finite number of bits, okay? And so it is helpful to remind ourselves that computers store numbers in bits, okay? Ones and zeros, just at the kind of the fundamental level of how a computer operates. Numbers are stored in binary. So if in binary you have this, what is this in decimal? This is 5, right? Because this spot represents 2 to the 0, this spot represents 2 to the 1, and this spot represents 2 to the 2. Okay? And so this means we have 2 to the 2 plus 0 2 to the 1s plus a 2 to the 0, so this is a 4 plus a 1, and we get 5, right? Is that okay? All right, and with a little bit of practice, you'll get this binary stuff down, okay? Now, we can also represent fractional values in binary. Okay, so what if I have 1.01.1? Okay, so this is not called a decimal point. It would be called a binary point to indicate that we've got fractional values. Okay, and what would this number be in decimal? Just say something. 5.5, right? 5.5, okay? Because over here we established that this is 101 would be 5, and this spot right here would be 2 to the negative 1 place. Yeah? Is that good with everybody? Okay, so then what would this be? If you have this in binary, in decimal, this would be 5.75, right? Because this is 2 to the minus 1, or 1/2, and this is 2 to the minus 2. So we have 5 plus 1/2 plus 1/4, and this gives us 5.75. Okay, and so this is what we have. We want to be able to represent numbers with fractions, okay, in binary, and we want to be able to store this in the computer, okay? And so to do this, we would take, let's say we're going to take our number 1.011, which we said was 5.75. We're going to put this into scientific notation, okay? So how does scientific notation work? Yeah, so the first digit, we're not going to have you don't have a leading 0, but we're going to just move our not our decimal, but our binary point over, and we're going to have this, right? We've moved this over, and so we're going to say this is now, because it's in binary, it's not going to be times 10 to the whatever, it's going to be times 2 to the 2, okay? Which, or in binary, is 10, right? To indicate that we have moved this over 2 spots. Okay, and we can just double check that this indeed works out, okay? This is this would be 1 plus, and we have 1 to the 1 times 2 to the negative 2 plus 2 to the negative 3 plus 2 to the negative 4 times 2 to the 2. Is this okay? And so this becomes 1 plus 1/4 plus 1/8 plus 1/16 times 4, and this is I don't know what this is. 1 and 7/16 times 4, or 1.4375 times 4, and we get indeed 5.75. Okay, but we're basically going to use scientific notation in binary. Okay, so we've got binary scientific notation here, and this is how we're going to try to represent values in the computer using binary scientific notation. Is this okay? Any questions on this? We're good? Okay. So, how can we do this? Well, we are going to, I'm going to use, for our teaching example, well, actually, okay, let me back up. So, in the computer, and R's default numeric method is double, okay? This is R's default numeric method, and this is, we might call this a double precision floating point number. Okay. And in the computer, this we will use 64 bits to represent a number. Okay, we uses 64 bits to represent a number. And those 64 bits are broken into kind of 3 parts. We got 1 bit for the sign. So whether it's positive or negative, 0 for positive, 1 for negative values, okay? Then we have 11 bits for the exponent. Okay. 11 bits for the exponent because it's in scientific notation. And then the remaining 52 bits for the what we call the mantissa or the significand. Okay. And so we use 64 bits to store a number. Okay, and again, just think of floating point as representing numbers in binary scientific notation. Okay, that's all we're going to do. Okay. Now, this try to do this lesson with 64 bits would just be too complicated. Okay, so for a teaching example, I'm going to just simplify this, and we're going to use 8 bits to represent numbers. Okay, and it's the exact, it's almost exactly the same as this IEEE 754 standard, except I'm just using 8 bits, but we'll use the same concepts. Okay, so our teaching example, we'll have 8 bits to represent a number. Okay, so it'll be 1 for the sign. We'll use 3 for the exponent, and the remaining 4 for the mantissa. Okay, and you'll see very shortly that nobody would use 8 bits for floating point representation. It's just too few bits for it to be useful. Okay, but we could use it in this example, and we'll make good. We'll do good with it. Okay, and so I'm going to represent numbers kind of like this. I'll say our 8 bits will kind of go like this, and I'll say, okay, and this is the sign, the exponent, and the mantissa. Okay, and so our previous value, which we had was 5.75, we said was 101.11, or in binary scientific, we said this is 1.0111 times 2 to the 10. Right? So we established this earlier. Okay. And so in order to represent this in our computer, okay, we've got 8 bits to represent this number. We can do this. Okay, it's positive. So what do we use for the sign? We're going to put in a 0 for the sign bit. Okay. Now we can do a little trick, and that is because in scientific notation you will never have a 0 in the leading digit. Right? You'll never have a 0 there. Okay, it's always going to be a 1 because if the leading digit was 0, that's not how it works. And because it's binary, if it's not a 0, it's always going to be a 1. Okay, so there's no need to actually store this 1 here. Okay, so we can kind of just assume that this is always going to be a 1. And so our mantissa will be just the trailing digit. So we'll put in 0, 1, 1, 1. Okay. Is this okay? So maybe I'll just highlight this. And so this part comes right here. And then the exponent, we'll then put in the exponent position. and we'll do 0, 1, 0. Okay? This is how we might represent the thing here. Yes, question?
How did you find the 10 on the 2 digit?
Oh, because in order to move this over, we moved it over. It's not a 10, it's a 1, 0, okay? it's a 2, okay? It's a binary. So we moved it over 2 positions, right? Okay, so we moved the decimal spot over 1, 2 positions, and so in binary we're going to indicate that we moved it over 2 positions by using 1, 0 to indicate that we've moved it over 2. Okay, if we moved it over I don't know, three spots, you know, we would have to say 1, 1, okay, to say we moved it over 3 spots. All right, is this okay with how this so far so good? Okay. All right, the old joke is there are people, you know, those who get binary and those who don't. Okay, that's haha. All right. Okay, so I'm going to illustrate that we have to make a slight adjustment to the way we represent numbers, though. Okay, so what we had here, what did I just do? Something happened. Okay, so this is a valid way to represent this, but we're going to have to make a slight adjustment, and I'll show you just now. Okay, so let's say we have the decimal value 0.5, okay? And we want to represent this in binary using and floating point, okay? So in binary, this would be what? 0.1, okay? And then, and now if we go into scientific notation, what do we have? We've got 1.0 times, I'll just do 1.0 times 2 to the -1, right? Okay. So we want to we now want to represent this in floating point notation, okay? So we wish to represent this in floating point notation. So what do we do? Okay. So our sign, this is 0. In our mantissa, this will all be zeros here, right? Okay, but now somehow we want to represent -1 in our exponent, okay? Okay, and so to do this, we're going to use what we call a biased scheme to represent integers, okay? So we're going to use to do this, we're going to use a biased scheme. So we have 3 bits for the exponent. Okay, so what is the greatest number of values? How many values can you represent with 3 bits? You can represent 8 digits, right? You can represent a total of 8 digits, and those would be 0 through 7, right? Okay, so 0 would be 000, and you got okay, so those are the 8 different values that you can represent with 3 digits. I mean 3 bits. Okay, and so what we're going to do is we're going to introduce a bias. If we want to be able to represent both negative and positive numbers, we have to introduce a bias. Okay, so to represent both negative and positive, we add a bias of 3. Okay, and so now 0, 0, 0 will represent negative 3, and these will be the values that we have. Okay, and that's all we're doing, is we're just kind of shifting these numbers so that, oh, if we want to represent the value 0, if we want to represent the value 0 with our bias scheme, we would encode it as 0, 1, 1, which looks like a 3, but there's an implicit bias of negative 3. So now, how do we pick this bias? The bias we generally set to be 2 to the n minus 1 power minus 1. Okay, so we say, oh, well, 3 digits, you can represent a total of 8 numbers. Okay, we probably want half of those to be positive and half to be negative. So 8 divided by 2 is 4. Okay, and then we just take 1 away from that. So rather than subtracting 3, our bias will be, rather than subtracting 4, our bias will be subtracting 3. Okay, so in order to represent this value of negative 1, okay, so the exponent here is minus 1. So with the bias, okay, we will enter which is, so we're going to put this in here, 0, 1, 0. And that's what we will have. And this allows us to have both positive and negative exponents. Okay, which is important when you want to represent decimal values. Okay. All right. So in double precision, what is the bias we would use? So in double precision, we have 11 bits for the exponent. So the bias we would use would be 2 to the 11 minus 1 minus 1. So we'd say with 11 bits, you can represent a total of 2048 values. Okay, 2048. We would half that, and we would get 1024, and we subtract 1. And we would say our bias is 1023. Okay, and in double precision, our bias is 1023. Okay, and so all in at the, and this is happening at the hardware level in your computer, as there's 11 bits to represent the exponent. And whatever value comes out of those 11 bits, we, have a bias of 1023 in them as well. Okay, in order to represent both negative and positive values for our exponent. Okay, and so on the previous page, with the bias, okay, the actual value would be what? Okay, so we would want to add 3 to this. So in order to represent the value 2, we would represent it with a 5, and we would have 101 with the bias. Okay. Is that okay? All right, so let's try out an exercise here. Okay, so let's represent the following decimal value in floating point as bits. Okay, represent the following decimal with 8-bit floating point. So we're going to represent 0.5625. Okay. So this 0.5625, this is, you can do 0.5, which is 2 to the negative 1, plus 0.0625, which is 2 to the negative 4. You guys want to try this on your own, or do you want me to just walk you through it? Walk you through? Sure. Okay. I asked the class last session, and they struggled trying it on their own. Okay. So in binary, how would we do this? Okay. What would this be in binary? With not scientific, but just in binary, it would be 0 point. We would have 1 in the negative 1's place, and then we would have 0, 0, and then we would have a 1 in the negative 2 to the negative 4 place, right? This is okay? Because it's 0.5 plus 0.0625, which is 2 to the negative 4. So this is what it is in binary. Okay? And then in scientific, what would this be? 1.001 times 2 to the negative 1. Okay, so we can start filling out our 8 bits. Okay, so what can I put in my my bits right now? I would put in a 0 for the sign, and then for the mantissa, I would put in 0010, right, to capture this part. Okay, and then so to the exponent is -1, okay, and we want to put in our bias here, right? So we're going to add 3 to it, and this would give us 2, okay? And so we would encode our 2 as a 010, and we would put that in there. So this is our exponent, which is 2, but then when we take away the bias, we understand that it's -1, okay, in our mantissa. Okay, and so this is how we might represent the value 0.5625 with an 8-bit floating point number. Yes, question? Which one? This exponent right here?
Yeah.
So the exponent in scientific notation is -1, right? Okay. We want to include a bias, okay? Because we can represent a total of 8 different values. We want some of those to be negative and some of those to be positive, so we're going to put in a bias of -3. Okay. And so to go from the decimal to the binary, we would add that bias to figure out what thing we want to encode. When we go from the binary to the decimal, we would subtract out the bias to get back the actual exponent that we want. So in this case, our exponent, the real exponent is -1. After we add the bias of 3, the biased exponent that we can include in our number is 2, which is represented with 010 in binary. Okay? Is this okay with everybody? All right. Okay. According to the standard, the IEEE standard, values outside of our range will be represented as infinity and negative infinity. Okay, so to represent infinity, okay, so if all the exponent values, exponent bits are 1, and all the mantissa bits are 0, that is infinity. Okay, so if you have if you have 0 and then 1, 1, 1, 0, 0, 0, 0, this is positive infinity. And then if you have a 1 here with a 1, 1, 1 and a 0, 0, 0, 0, this is negative infinity. Okay, if all the exponent is 1, and you have a non-zero in the mantissa, then it is not a number. Okay, so not a real number. And so we would say this is, something like this would become not a number. Okay, if this is not all zero. And then the other things is all zero, all one. Okay. And this is just part of the standard, and this is what the IEEE group decided. This is how we're going to represent numbers, okay? And say if all the exponent bits are 1 and it's all 0, then it's either positive infinity or negative infinity depending on the sign bit. And then if you've got all 1s in the exponent and then and then something that's not a 1 in the mantissa, then it's not a number. Okay. All right. So with that in mind, what is the largest value that we can represent with our 8-bit floating point? Okay. Largest value in 8-bit floating point. Okay. Well, the first digit will, the first bit, our sign will be 0, right? Because it's going to be positive. Okay. What will our exponent bits be? Not 0. It will be 1, 1, 0, right? Because we can't have all 1s in the exponent, because that would indicate either infinity or not a number, right? So this would be largest exponent that is not infinity or NaN. Okay, and then what would be the largest mantissa we can have? The mantissa, there's no bias in the bias. It would just be all 1s, right? This would be the largest mantissa. Is that okay? Okay, and so what value does this represent in decimal? Okay, so this would be, a positive 1.1111. Okay, using our mantissa there, times 2 to the, what's 110? 6, right? But we have to include the bias and subtract off 3, right? So this is going to be 2 to the 3. Okay, so this is 110 minus the bias. Okay, so what is this? This is 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16. Is that okay? Times, and this becomes 2 to the 3, or 2 to 8. Yeah, question?
Where did the extra 1 come from?
So, you mean this one right up here?
Yeah.
So the thing is if it's in scientific notation, we know that the leading digit is always going to be a 1. Okay? Because when you put things in scientific notation, you never have a 0 as the leading digit. And because if the leading digit is always going to be a 1, there's no need to waste a bit to indicate that. Okay, so as back in the day when people were trying to figure out how to store numbers in computers, the bits were precious, right? Now we got 8 gigabytes and we don't really care what we do with our memory, and there's nobody cares about optimization, right? But you're trying to program Mario on like a 5K chip. Like every bit is precious. So we didn't want to waste any numbers spent to say like this first number is a 1 because it's always a 1, right? So it's implied that this first number is always a 1 here. Okay. All right, so we have this, and this becomes 1 and 15/16 times 8, and that is 15.5. So this is our largest value. Largest value with 8 bits. Okay, 8-bit floating point notation. Okay, and this is why I said nobody would use 8 bits in reality, because it's just, if the largest number you can store is 15.5 and anything bigger than that the computer says is infinity, it's not a very useful system for numbers. Okay, so the computer uses, you have single precision, which uses 32 bits, and our default value is a double precision, which uses 64 bits to store a number. Okay, and so with in double precision, the largest value would be 0, and then you have 11 bits here, and then 52 bits that are all 1s. Okay, this would be the largest largest value that we can call, and this would this is sometimes known as real max, and on our computer you can get it by asking dot machine in R. Dot machine $, I think it's double X max, but I'll ask. Okay, so over here we say type in dot machine. Okay, and so this is at the machine hardware level, and we have dot machine double.x max. Okay, and that's about 1.78 times 10 to the 308 power. It's approximately 798 times 10 to the 308 power. Okay, and so that would be the largest number we can represent using double precision. Anything bigger than that, the computer just says, "Ah, that's infinity." Okay. And again, this is at the heart of it is because there's an infinite number of real numbers. We have a finite number of bits to represent a number, and so there's only a finite number of values we can represent. All right, so far so good? What if I showed you, what if we want to represent 0, okay? How to represent 0. Okay, well, we would naturally think that something like this should represent 0, okay? Okay. But with our current rules, what does this number actually represent? Okay, so with current rules, this would actually be 1.0000, right? Because we said we're always going to assume that this is a 1 times 2 to the 0 minus 3, 2 to the negative 3. So this becomes 1 times 2 to the negative 3, and this becomes 1/8 or 0.125. Okay, so this is a problem. We need to be able to represent 0. Okay, so in order to represent 0, we have to complicate our rules a little bit. Okay. And we say if the exponent is all zeros, okay, we are in what we call a denormalized situation. We are in a denormalized situation, and this means the leading digit is not 1, but is now 0. The leading digit in our scientific notation okay. And that will happen only if the exponent is all 0. Okay? And so in this case, then it works. Okay? So then, so 0, 0, 0, 0, 0, 0, 0, 0 now becomes 0.000 times 2 to the 0 minus 3. I'm sorry. It's actually going to be 2 to the 1 minus 3. And this is going to be 0. Okay? In denormalized situations, the exponent, okay, if all the exponent things are 0, okay, the exponent to use will be 1 minus the bias. Okay, so in this case, -2. Okay, and so if your exponent, so basically if exponent is all zeros, then the leading digit is 0, and the exponent to use is 1 minus the bias. Okay, so what does this mean on a practical level? Well, let's take a look. Okay, so we can represent 0 using all zeros. What will be the smallest non-zero value we can represent? Smallest non-zero value. Okay, the smallest non-zero value would be 0. We would have all zeros in the exponent, and then our mantissa would be 0, 0, 0, 1. Okay, and so this would be 0.0001 times 2 to the, and when you have all zeros for the exponent we're using is going to be 1 minus the bias. Okay, so this is 2 to the -4 times 2 to the -2 here, okay, or 1/16 times 1/4, and we get 1 over 64, or 0.015625. This is the smallest non-zero value we can represent. Okay, and then the next smallest would be 0, 0, 0, 0, 0, 0, 1, 0, right? And this would just become, if we do our calculations, we would get 2/64 or 1/32. Okay, so we're incrementing by 1/64, and then the next would be that would be 3/64. Okay, and then we can get up to our largest denormalized, which would be 0, 0, 0, 0, 1, 1, 1, 1. And what would this be? This would be 0.1111 times 2 to the 1 minus 3. And this turns out to be 15 out of 64. Is this okay with everybody so far? All right, what would the next number in our sequence be? Okay, so previously we had our largest denormalized. This is 15 out of 64. And then, so now we are at our smallest, and now we are in the normalized section. We would have not zeros in our exponent. We would have the smallest exponent we can have, and this would be all zeros, right? So this would be times 2 to the 1 minus 3. This is 1/4, or we can also say 16 out of 64. Okay. So naturally, you know, we're gonna keep climbing this way. Is this okay? Okay, and then you know we continue on, and then the largest value in this with this exponent would be 1.1111 times 2 to the 1 minus 3. And if you do the math, we would get 31 out of 64. Okay. All right. And so let me just show you just something interesting happens at this point, okay? So the next value in the sequence here, we would kind of get up to this point, which would be 1.0000 times 2 to the, and now we're at 1.0, or 10, so 2 minus 3. And this becomes 1 times 2 to the minus 1, which is 1/2, or equal to 0.5. Is this okay? And a tiny bit something interesting happens next, okay? What is the next number in our sequence? We would keep our exponent, 0, 1, 0, and then the next value here would be 0, 0, 0, 1, right? Okay, so this becomes 1.0000 times 2 to the 2 minus 3, okay? Whoops, no. This is a 1 at the end, okay? Okay, and so this is 1 plus 1/16 times 2 to the negative 1, okay? And so this becomes 17/32, or 0.53125. Okay, and so up until this point, each bit increase increments by 1/64. Okay, once we reach this point, we are incrementing by 1/32. Okay, we cannot at this point we can no longer distinguish 64ths or things smaller than that. Okay, and so one of the properties of floating point is that values close to 0 are very close together, but as the numbers get bigger and bigger, we lose the ability to distinguish such precision. The numbers get more and more spaced out. Okay, so values close together, or values near 0, are close together, and then larger values are spaced out. Okay, because we have a finite number of values that we can represent with our finite number of bits, and so, but we're still trying to span the entire, as much of the real line as we can, right? And so, you know, if our real max is something around 10 to the 308th power, and we have a total of 2 to the 64 digits that we can represent, or values we can represent, it makes sense to space out the really big ones and keep the really small ones together. This causes some interesting things though, okay? When you start R, you might see things like, okay, what is 0.1 plus 0.2? And it says, oh, that's equal to 0.3, okay? But you can ask, is 0.1 plus 0.2, is that equal to 0.3? And what it says is that, no, it's not equal to that, okay? So what's going on, okay? Well, we can do something. We can set our digits equal to, I think, 17. This is, the machine epsilon is approximately equal to about 17 digits in decimal, okay? And if we ask what is 0.1, it's not actually 0.1, okay? Because there's only a finite number of values we can represent on the real line, the closest binary scientific number we can represent is not actually 0.1, it's a little bit off from it, okay? 0.2 is also a little bit off. This is very close to the value we're asking, but it's not exactly equal to it at the binary level, okay? And if we ask what is 0.3, it's not exactly 0.3 either. It's 0.299. And so if we say what's 0.1 plus 0.2, these values are different, and that's why the computer says these two things are not equal, okay? So you have a function called all equal, and this says if two things are very close to each other, okay, within what the machine, what R deems to be a tolerance value, it's going to say they are equal to each other, okay? And so, so we have to be mindful that when you represent that numbers in the computer do not behave like the real numbers that you are used to working with in math, okay? In math, you can multiply things out of order, add and subtract things, in different orders, and it doesn't matter. In computers, the operations you do actually do matter because it throws certain things off. Okay, we'll talk a little bit more about this, but it's important to remember that computer numbers are different from real numbers.